Okay, let's go with the final session for today. So I want to continue talking about ruthenium catalyzed reactions and metathesis, but we're looking at a couple of special cases here involving alkynes. And the pathway, well, the basic mechanism is the same, but the outcomes look slightly different. So let's think about, in the same way as we started with ring closing metathesis, RCM, with alkenes, let's think about what if one of those alkenes was a triple bond, so ene-ine ring closing metathesis, sometimes called EYRM. So here, drawing the same schematic as I drew before, one alkene, one alkyne, in the presence of ethene, and we'll see why that is in a moment, then yes, you ring close, but for some reason or another this has got shifted, the right and left have got shifted here, but this extra, if you try rearranging the bonds, you don't actually completely break this triple bond. You will break the two bonds, but that will leave one behind. So that part is still attached, at least it's color-coded correctly, even if it's moved left to right. And you end up actually, if you didn't have the ethene there, you'd end up with a metal here, and you need some way of finishing the cycle. So you have ethene in here to close it off. If it's a cross metathesis, then you're putting in another alkyne, and that ends up here. That's a wavy line just to show that you could get cis or trans at that point. So you either have, so these are not so different really. You could either have ethene as the sort of terminating alkene, or you have some other alkene. So what you're doing is you're joining the two carbons together, if you like, at the inside of the system, just like in the convention, the normal alkene metathesis, but then because you've got a triple bond, you've got a little bit left over, and you need another alkene to do a metathesis and finish that off. Now it doesn't have to be ring closing, so here's a case where you take an alkyne and a separate alkene that's not joined to the alkyne as part of it, with a tether between them, and ethene, and here is the product. I'll ignore that box for now. So the linkage of the alkene to one of the, the alkyne, I should say, to one of the alkenes corresponds to the ring closing metathesis, and then this double bond CH2 corresponds to it being capped off with ethene. So we should see how that, well, here's some other examples. So here's one from Grubbs himself. These two side chains are on the same side of the 5-membered ring. So the 5-membered ring ends up here in the product, and underneath you get 1, 2, 3, 1, 2, 3. So this is the remains of one side chain, and and then here's the leftover bit from the alkyne with ethene closing off, finishing the process off. And another one down here where the same thing is going on. So 1, 2, 3, yeah, okay. And again, this CH2 here is coming from ethene at the end of the process. So you're doing a ring closing metathesis with a bit of a side chain left on. So let's see if we can work through how that might happen. So we're trying to go from here to ring close with a double bond, and then the bit that's left over, because we're not breaking all the bonds of the alkyne, is the red part, and then the ethene is finishing it off. So we're starting the same way. This is meant to represent, well, it's shown as Grubb's first generation, but it's meant to represent one or other of the ruthenium carbene catalysts. A cycloaddition to the first alkene, breaking down in the opposite direction to the way it was formed, to give you a, that's a ruthenium there, to give you a ruthenium carbene and styrene. Then cycloaddition here, which gives you a metallocyclobutene rather than a metallocyclobutane. So it's an unsaturated metallocycle instead of a saturated one. So if you then break that down crossways, then you'll have the ring closing metathesis double bond, as we've seen previously, but you still have this bit of the alkyne left over because one of the 3 bonds in the alkyne is still there. And you've got a ruthenium carbene on that branching chain. And that's why the ethene is there, because it's doing a conventional metathesis, as I could call it, between this ruthenium carbene and another alkene, cycloadduct, break down the opposite way to give a double bond, and a ruthenium carbene that can go back in at the start, or as a CH2 carbene, or it can exchange with this one to go back to the same original carbene. But basically, you regenerate a carbene here to go round again. So that's how you get the, what I might call the standard metathesis, and then the extra bit, because the alkyne here retains one bond from itself, and you need to do something with the ruthenium species that's on it. Hence the need to put in another alkene. So it really follows the same pattern as before, and the difference is the fact that with the alkyne you get this double bond in the metallocycle. But you do the same things with it, so you can think about it and you can develop this sequence in the same way. Here are some cross metathesis examples, 2 separate ones, not forming a ring. So here, the only other alkene used is ethene, and that's being used both for the metathesis with alkyne and for the finishing off metathesis with the bit that's left over from the alkyne. So here's the original, the standard metathesis, and here's the final one finishing off. So you need obviously an excess of ethene in that case. Here's another mixed one. Initial cycloaddition would happen on this bottom alkene, cyclo then breaks down to give double bond ruthenium down here instead of double bond carbon. That adds across the alkyne, and then that breaks down to give you this. Now this alkenyl ruthenium carbene, and then that does the cross metathesis with another added alkene, because there's no ethene added in that case. And if you work through that mechanistic sequence, you'll see where these come about. In fact, probably I would still have to write down the intermediates rather than being able to write down the products directly. But if you understand the sequence in the mechanism, then you should be able to work through to the products. So this is showing the same thing for having a different alkene added in. So this is very, very similar to the last case. Cycloaddition of the catalyst carbene to the first alkene, breakdown of that first metallocycle to give a ruthenium carbene, which then cycloadds to the alkyne to give you the unsaturated metallocycle, which breaks down to give you the metathesis, the standard metathesis and the branching chain. And now instead of that being finished off by ethene, as we saw in the previous sequence, now a different alkene intervenes, does a cycloaddition, breaks down the opposite way, and finishes off the sequence to get up here. But a bit like those Stille, Suzuki, Negishi, etc., it's all basically the same mechanism, and you just deal with whatever components you have in the reaction vessel.
But if the reaction starts with alkyne first,
I think it's known that the cycloaddition onto the alkyne is slow for the primary cycloaddition. I'm pretty sure that they've done cases where there are two alkynes, and that's a very slow reaction. In some of these, you can actually isolate the initial, or get spectroscopic evidence at least for the initial metallocycles. There's evidence of which, even if it's two alkenes, there is evidence now that you can predict which of two alkenes will add fastest to the ruthenium. Certainly the least substituted alkene will always be faster than a more substituted one, but I think I'm pretty sure that it's known that alkenes add faster than alkynes.
and some intramolecular possibility.
Sorry?
Intramolecular alkene alkyne.
Oh yeah, that was that was what we had. Yeah, that one. That's the one we looked at before. Yeah, so yeah, definitely intramolecular possibilities. Oh, I suppose, yeah, I mean that's what's shown here, isn't it? I beg your pardon. Yeah. So the difference between this and the previous scheme is just what alkene you finish off with when you've got your ring closing process, and then you haven't just lost everything outside the ring. You've got this bit here that retains one bond from the original alkyne, and you've still got a ruthenium carbene, and you need to finish that off. And it just depends on whether you've just got ethene around or whether you've added some additional alkene. So here are some examples of different metatheses. So here you're getting an ene-ine metathesis here and there, and then the leftover carbons on the middle are metathesizing together, and ethene has gone, basically. No, no, it hasn't actually. Yeah. Ooh, I'd have to work that one through. I can't see it for the moment. Right. I should have left that as a tutorial problem so you could work it out. Can't quite see if that's... Yeah, that looks like everything's still in the product. Anyway, okay. This isn't an ene-ine one, but it's just this double bond here is ring opening, and then the alkenes you get here, and so you get an alkene, a vinyl group if you like, here, and they're joining together to give the double bond that's making this 7-membered ring, and then the that carbon and that carbon that are further out are ending up as vinyl groups. So that's a cross metathesis with ethene. On each of these double bonds is ring opening these two non-borane systems, and then the pendant groups that are a long way apart from each other are these two here, and the pendant vinyl groups that are closer to each other here and that will be here and here are joining together to give the 7-membered ring, and again recovering ethene. And again here, this is a ring opening going on here, and then a cross metathesis of the vinyl group here with this side chain, which is a very good partner in cross metathesis, and the vinyl group that's at the bottom end of this cleaving double bond ends up down here on the 6-membered ring. I'll have to work through that one. I can't quite see it at the moment. Okay, well that's the alkynes, and finishing off with those other more unusual ones are sort of slightly extensions of the traditional standard metathesis. So I want to finish off this won't take very long, looking at gold as an activation of alkynes. So I said I was going to deal with palladium, ruthenium and gold. The gold part will be quite short, but just introduce the idea that gold is good at activating alkynes. Now people would say, why would I use gold? It's very expensive. Actually, gram for gram now, gold is cheaper than palladium, and certainly cheaper than some other metals like iridium and so on. So it's not as bad as it sounds to use gold as a reagent. It is catalytic. So remember the alkyne activation picture when I was thinking of the complexation. We've just assumed up till now that it's going to happen, but just to remind you of what I said, that we've got filled d orbitals, vacant other orbitals on the metal. So, and then we can get pi orbitals as filled, which can interact if the alkyne goes sideways, so to speak. Then the pi bonding orbitals can interact with, or at least one of them can interact with the vacant metal orbital, the filled d orbitals can interact with pi antibonding orbitals. So alkynes, same as alkenes in that sense. So what this does is it gives activation of alkynes towards a variety of nucleophiles under homogeneous conditions, as long as you use a soluble type of source of gold. So here are some of the gold chlorides, gold 1 and gold 3 and so on, that are listed down here that are used. So what the general scheme is that the alkyne complexes to the gold derivative in this kind of fashion, that then a nucleophile attacks, and that leaves the gold effectively covalently bonded at one end of what used to be the alkyne, and then various things can happen, and what I'm showing here is loss of the gold when protonation happens at that center. So it's an activation of an alkyne to addition of nucleophile and hydrogen across the alkyne, which is normally, this is electron rich enough that you wouldn't expect a nucleophile to be able to add, but effectively the withdrawal of electrons in complexing with the gold means that nucleophiles can add. So that's the use or the value of this type of activation. So here's an example of what might be done there, just hydrating alkynes, which is not a new process, but has always required either forcing conditions or has been quite slow and low yielding. So with gold activation, this makes this a much more sensible process. So gold activates, water adds, could realistically, and I've drawn an unsymmetrical alkyne here, could add at either end. So you could get one of two different hydroxy adducts, and of course this adduct is an enol, or a gold derivative of an enol. If you proto-deorate that, protonate with loss of gold, then you would put a proton where the gold was, so you've overall added water, although you're going to lose that geometry shortly, in one or other of the regiochemistries. Now, in a particular example, you may, the situation, the substituents may favour one orientation of addition over the other. But in principle, if there's no particular bias in the alkyne, you should eventually end up with a mixture of ketones from hydration. In principle, you could think that this should be able to produce enol ethers, but I'm not sure that whether that's known yet or not. But you could imagine other nucleophiles. This is a very simple case of speeding up a reaction that has been known for a long time, but has not always been practical. So here are some other examples just to show how this sort of thing has been used. So here's one where the nucleophile is a carboxylic acid oxygen and is adding to an alkene here. Well, sorry, adding to an alkyne here to produce an alkene. It's adding at the inner end to make a 5-carbon ring. Here to make this cage structure, in fact both of these, so not only is the alkyne being activated and one OH can add, but actually then the gold is sticking around to activate the alkene for a second attack. And so you get both of these CH2OHs, both of these oxygens actually going on to first the alkyne and then the alkene here. This is a nitrogen nucleophile. So again, we're activating with a gold source, and that is allowing the nitrogen to interact here. And then the gold is being removed by protolysis, acid workup, as you might say. And then one more, where the nucleophile is a carbon nucleophile. So there's always going to be some enol in this mixture, so there is always going to be some nucleophilic potential at this center between the two carbonyls, and that is enough that's nucleophilic enough, as long as we've got gold activation of the alkyne, to bridge across and form the 5-membered ring.
In the third reaction, what about the steric region, steric vectors?
Here?
In the rectangle. Spherically.
Yeah, I think this one has no. Oh, you mean this is very hindered? Yeah. You'll notice in all of these, I'm not sure how general rule it is, but in all of these, the gold is added to the least hindered end of the alkyne, and the nucleophile is adding to the other end. So I think this must be, well, partly I think it probably couldn't reach the other end because of the steric constraints in this structure, but to fit with all of the others, if the gold wants to end up at the least hindered end, then the nitrogen will go where I've shown there. You'd need to build a molecular model to see how flexible this system is. I think this is probably quite inflexible. So as I say, in each of those, the nucleophile is added at the substituted end of the alkyne, and the gold at the other end. I don't know how general that is, but it's certainly true of all these examples. Let's have a look at these examples. Oh, these are alkenes. This drawing it looked better on the computer screen than it does here. So that dot there is a carbon. So this is double bond, double bond. This is an alkene, and gold is activating that as well. So that's quite a reactive kind of alkene, and we've got here the indole nucleus acting as a nucleophile through its C3 position, and that's effectively an enamine. So the nitrogen lone pair pushing in, electrons coming out, nucleophilic potential at the 3 position, and then adding across the terminal position of the allene, or adding to the terminal position of the allene. Gold will have added to the internal position, so you get a vinyl gold intermediate that then on acidic workup is being protonated to give the hydrogen that is at this position. This is the second reaction is the same thing with a nitrogen nucleophile instead of a carbon, an enamine type nucleophile. This is the nitrogen of aniline doing the same thing effectively. Here is an amine which is part of a carbamate system, and so it's a little bit different to the one above, but not so different. And again, it's adding to the terminus of the allene, and the gold will end up at the middle and then is being protonated away. And likewise here, where an alcohol is the nucleophile, and again it's adding to the terminus of the allene, and gold is at the internal one. Now, I'm not quite sure here, I'm I'm not quite sure about the regiochemistry here, because that looks like the nucleophile has gone for the more hindered centre, and maybe again it's because the gold, well, I don't know, why isn't the nucleophile adding at the bottom end? I'm not sure. I'm not sure about that. I guess you could argue that if the top half of the allene is being activated, that gives you a better delta plus on the tertiary position here. So the bit of carbocation character here is what's driving that, because that will be the position more able to accommodate a delta plus. And here are some examples of the gold chemistry being used in complex natural product synthesis. These aren't all allene. Now this one's an allene one again. So this time the 3 position of the indole, which we saw as a nucleophile before, isn't available because that's already occupied. So the 2 position can be a nucleophile, and there it is closing onto the terminus of the allene with the gold going on the middle. Of course here, when you're forming a ring, it's not really going to be able to reach the other end of the allene, so there's no particular issue with it closing onto this left-hand end as drawn. And that's going to be the left-hand side of this particular natural product, and clearly there are some carbons that are going to be modified. Where are we? Oh no, sorry, I beg your pardon, it's the right-hand side, turned on its side, I beg your pardon. Yeah, so you do want this extra ring here, which is there. In this bryostatin, marine natural product, this is the bond that's being made, and that's this oxygen acting as a nucleophile on this alkyne. So this is a straightforward case, if you like, of an activation of an alkyne, and it's a question of which ring size, and clearly the 6-membered ring is winning here. What's happened to this one? Oh, this is the work my way through that one. Okay, so this is the nucleophile, this alkene, and there was the triple bond. So the terminal position has acted as a nucleophile to form this bond here. Crumbs, I'm not quite sure where what's happened there. Okay, that's in the natural product. Oh, I'm looking ahead of myself. Okay, so yeah, okay, so that's a carbonyl. I'm still lost. Oh, okay, right. So that, yeah, okay. So the top, this double bond has acted as a nucleophile towards the alkyne, and then that would give a double bond here. So it's the product is effectively an enol. So it's reforming into a ketone. The penalties of just copying these things without looking too closely. So you can see that certainly the middle one, I think that's a fairly straightforward one, and this one, that one has confused me slightly. So you can use this activation of alkynes and of the double bonds in alkenes, which are very reactive, and there was a tandem one where an alkene was also activated earlier on. So gold as an electrophilic activator of alkenes, or multiple bonds, so that they can have nucleophiles added to them. And that may be the end, I think. So that is the end, ending on a confusing note down here. So that's lecturing a bit on ruthenium and a little bit about gold as an activator for multiple bonds. There is, of course, a range of other organometallic chemistry, but I've tried to pick out some of the key features, or the more prominent features here, and shown you some more complex examples. So I've had one more lecture tomorrow morning, which will deal with the use of some of this chemistry in natural product synthesis, so some sequences I will talk through, and then we will have a tutorial session after that, and then that will be, so then by lunchtime we'll have finished the formal part of the course. We will have a brief test after lunch, 45-minute test after lunch tomorrow, but more about that in the morning. So that's it for today, and thanks for sticking with it for 4 sessions. Thank you.